So greetings, hello and welcome students. This is the video about phase lock loops and its applications, popularly abbreviated as PLL. This is the last unit of your course. So let us understand the concepts of phase lock loops and its applications. So before we learn PLL, we need to understand a couple of concepts. Like what is really a phase locking means. Now in phase lock loops, we use the term called as phase locking. So what is this phase locking is all about? Now in this slide, you can see two pictures. In first picture, you can see the case of phase locked, whereas in second picture, you can see that two signals are unlocked with respect to phase. So what's the concept? So here you can see that there are two input signals, V in 1 and V in 2. So both are in phase, and phase is exactly matching. So on time of V in 1 is exactly same as on time of V in 2. Off time of V in 1 is exactly same as off time of V in 2. So since these two signals are in phase, if we compare the phase and try to find out the difference between these two signals, the output is going to be 0. So this is what the phase locking means. So in phase lock conditions, the phase of both the signals are exactly matching. You can say there is 0-degree phase shift. Whereas in case of unlocked phase, you find here in second picture that second signal is delayed, shifted, and that's why there is a phase difference between first signal and second signal. Although the frequency is matching, both the signals are having same frequency, but there is a change in phase, shift in the second signal, and that is why you can see that when you compare these two inputs, you get the output which is corresponding to the phase difference between these two signals. So this case, we can say that these two signals are unlocked as far as phase is concerned. So later on in phase lock loops, PLLs, basically PLL is a loop. Okay, so there is going to be a feedback action, but all this looping action is just to lock the phase, and that's why it is abbreviated or it is called as phase lock loop. So we need to understand the concept of phase locking. So hope from this picture the concept of phase locking is clear. Okay, so phase locking, in short, they are in phase, both the signals are in phase. That's why if we try to find out the output voltage which is proportional to the phase difference, it is going to be 0 when there is a phase locking condition. So let us move on to another concept which is also important in PLL. Now in PLL, if we have to compare this phase and generate the proportional output with respect to the phase difference, then we require a device called as phase comparator. So let us define and understand the concept of phase comparator. So phase comparator is a device which compares the phase of inputs and generates the output proportional to the phase difference. So here is the block diagram. So as you see in the block diagram, V in 1 is one input, V in 2 is another input, just like we have seen in the previous slide. And there is an output voltage which is proportional to the phase difference of these two input signals. So that is the construct of the phase comparator or block diagram of the phase comparator. So in the literature, if you see, there are prominently two types of phase comparators or phase detectors that you find. One is analog phase detector and another type is digital phase detector. Typical analog phase detector that you see in the literature is multiplier type of phase detector, which is widely used in communication systems. Now basically, we have not seen the concept of multiplier. This is something related with the log amplifiers, log and anti-log amplifiers. Now this we have not covered in our course. That's why we are not focusing on multiplier type of phase detector. But just we are interested in the understanding of the concept of phase comparator or phase detector. We are going to focus on the digital phase detector. The most popular phase detector, digital phase detector, is a XOR gate. Okay, so I am going to explain this XOR gate in detail. So this is what the phase comparison is. So we have input 1 here, input 2 here. Input 2 is phase shifted. Although both V in 1 and V in 2 have same frequency, there is a phase shift. And since there is a phase difference, as you see here, blue output, okay, which is corresponding to the difference between these two inputs. That is phase difference between these two inputs. Later, to convert this into proportional voltage, we can find out the average with the help of simple low-pass filter, and we can generate a proportional voltage which is directly proportional to the phase difference. So this is the whole idea of phase comparator. Let us see the typical digital phase detector, which is the simplest case, that is XOR gate. XOR gate you have studied in digital electronics. This is the symbol of XOR gate, and this is the logical function, logical output of XOR gate. So Y is equal to A exclusive or B. You know that it is A into B complement plus A complement into B. So here you find the truth table of XOR gate. So for 0, 0 inputs, we know that XOR output is 0. For 1, 1 also, the XOR output is 0. Only for this highlighted cases where you have two dissimilar inputs, output of XOR gate is always 1. So for 0, 1 and 1, 0 case, the output of XOR gate is 1. So this property of XOR gate, which generates the output for the dissimilar inputs, so this property is helpful to detect the phase between two inputs. So that's why in digital phase detector, you will find XOR popularly used as a phase detector. Okay. So here is a simple circuit actually simulated in multisim. So IC 7486, which is XOR gate, is used here. Two function generators will provide input 1 and input 2. Blue input is input A from this function generator. Red input is input B from this function generator. And output is shown in green color. So as you see here, when this is logic 1, this is logic 1, output is 0. This is logic 1, This is logic 0. So there is a mismatch. That's why output is 1. This is logic 0. This is logic 1. So again there is a mismatch. Output is 1. Now input A is 0, B is 0. For similar inputs, output will become 0. So this will continue. In short, because of its ability to detect the dissimilar inputs, we can use XOR gate as a phase detector. So remember, the output is proportional to the phase difference between two inputs. And as I told you on the previous slide, that you can later give this output to the low pass filter, which acts as an integrator or averaging circuit, and give us the proportional voltage directly.